Physics Chapter 3, Section 3 is dedicated to my girl, Annie Timmerin. Annie, wherever you are, I hope you enjoy this little video on free fall, which of course is acceleration due to the force of gravity alone. We have some essential questions here. Feel free to read them. Origin. Origin is a point at which the variables have a coordinated system value. We're going to look at free fall. We're going to look at free fall acceleration. Galileo was one of the first guys to really look at this idea of free fall when it's just gravity. Now he had to do some special tests to kind of neglect the force of air, because if you fall through the air resistance is going to slow you down. But if air isn't a factor, then it turns out that no matter how high you drop something, no matter how much it weighs, they're always going to accelerate at the same rate. We call this acceleration free fall acceleration. Near the surface of the Earth, we're going to give this free fall acceleration a special symbol. We're going to call it G, and G equals 9.8 meters per second squared. So right around 10. A lot of times you're going to find me using 10 instead of 9.8 just because it's easier to use 10, but 9.8 is the real number. When we're starting to look at free fall, whether you treat it as a positive or negative depends on the coordinate system you use. Let's take a little look at a video here. So, at the top of the flight, the ball's velocity is 0. Velocity is 0. However, it's asking what would happen if the acceleration were 0. You're saying, isn't the acceleration 0? No. If the acceleration was 0, then the ball would stop moving. It wouldn't fall down anymore. If this were the case, the ball would simply just hang in the air instead of falling. So the acceleration can't be 0. The acceleration still has to be downwards. Because this is not the way objects tossed in the air behave on Earth. You know that acceleration at the top of an object's flight must not be 0. You have to believe that, or you have to know that the object is falling even from that height. The acceleration is always going to be downward. There are some amusement park rides that use this free fall design. Usually you go up, you're suspended momentarily, and then they drop you and you plunge. When the cars are in free fall, most massive riders and the least massive riders, everybody has the same acceleration down. Suppose a free fall rider at an amusement park at rest falls for 1.5 seconds. What would the velocity be after 1.5 seconds? Well, if you start out at 0 and you fall at 9.8 meters per second squared for 1.5 seconds, 9.8 times a half, you get 15, right around 15. Now you can do this with a velocity time graph as well. I mean, again, here's all these equations, but I'm going to show you how to do this with velocity time graph. Now, astronaut David Scott went up to the moon, 1971, and he dropped a feather and something else, a wrench or something, and without the effect of any air up on the moon, they fell at exactly the same rate. They didn't fall at 9.8 meters per second, however. Reason why? Because it's the mass of the object that is falling towards the Earth or the moon that decides how fast it's going to fall. Distance an object is in free fall, it is responsible for the gravitational pull. The greater the distance, the less the acceleration. That's it.